Okay, so now we're going to do a very simple example, but an example that's very rich in interesting physics. And that's the example of a car driving around a curve that's banked. Okay, so what does that mean? So this is the car, zoom, zoom. It's going to be going around a circle like this. And this is the road. Okay, and so we're going to take that section of road and we're going to tilt it up. We're going to bank the road at some angle, theta. Okay, and then we're going to take that banked section of road and we're going to repeat it all the way around. Okay, so to construct a chunk of road that looks like a cone. Okay, and then that car is going to drive around the inside of that cone, always maintaining that same tilt angle. It's here, then it's here, then it's here, then it's here, then it's here. And so it is moving in circular motion like this, a circle in the horizontal plane, and always tilted at the angle of the tilt of the banked curve. Okay, so very good. So now in high school physics, everyone does the banked curve problem, and the banked curve problem is usually stated something like this. We have a road which is banked at some angle, particular angle, 27 degrees, and there's a coefficient of static friction between the tires and the road of, let's say, 0.82. And the question then is, and the radius of this horizontal circle is, say, 42 meters. The question then is, how fast, what is the maximum speed that you can go around that banked curve before you break static friction and the car starts sliding up, accelerating up as it's going around the circle, and hence sort of spiraling up like this and out. Okay, so that's one particular example. But remember, in physics, we are not really interested in solving particular problems like that. What we're interested in doing is taking a simple problem, like a car going around a banked curve, and solving the general problem for variable angle theta, variable coefficient of friction, and so on. Just get an algebraic answer so that we can look at it and sort of extract from it all of the interesting and beautiful physics. So we can ask, when we have general formulas, we can say, oh, what happens when the angle is 0? You know, what happens when we crank the angle up to, 90 degrees? Well, then that car can zip around at infinite speed without sliding up, and so on and so forth, right? So we really want to understand all of the physics, okay? And this example is simple enough. It's just a car going around a banked curve, right? And I just want to stress that going from a particular numerical example to the general case isn't any more difficult. Instead of writing 27 degrees, you write theta. But all of the algebra is the same. And the advantage is, like I said, you end up with an algebraic expression that you can sort of, play with and see, oh, that's interesting. When we do this, then that happens, and so on, right? So anyway, so this is the banked curve. So we're going to go through 3 steps in increasing complexity. So the first step is we're just going to imagine that there's no friction. Okay, we've banked it at some angle. There's no friction, and the car is not going around in a circle. The car just starts at rest. So then what's going to happen is we just have a block on a frictionless incline plane, and when we release it, well, it's just going to accelerate down the incline. There's no circular motion here. Just let it go, it slides down, accelerates down. Okay, so that's the first case that we're going to look at, and you'll see why later. Okay, so case A is car starts at rest. Okay, so when the car starts at rest, and I'm going to draw a little line in here to make sure I don't use up too much room. Because the most interesting part, example, the richest part will be here. Okay, so car starts at rest, and so what does our picture look like? Well, we've got a road which is banked at some angle like this, and so there's some banked angle theta from the horizontal, and we have a car of mass m which is sitting on that road. And we're going to say that the coefficient of friction between the tires and the road is 0. Okay, so right away that tells you that, remember that whenever an object is in contact with a surface that is frictionless, the surface can exert a force on the object that we're interested in only in a direction that is perpendicular to the surface. Okay, when it slides down like this, frictionless. So the surface can't exert a force that way, like a force of kinetic friction or whatever that way. So there's, sorry, yeah. So, yeah, that's it. Only a normal force. Okay, and so that's it. And so we know, obviously, if we let this thing go, it starts at rest, we let it go, it's obviously going to accelerate in that direction down the incline. So that's the direction of the acceleration. If that's the direction of the acceleration, then no matter what forces are acting on that thing, they better add up to a net force in that direction down the incline. Okay? So then you start thinking about, well, what are those forces? Okay, so let's draw it over here. So what we're going to do again is we're going to add up the forces. We're not going to use components. We're going to add up the forces just as vectors so we can see sort of geometrically what's happening with these vectors. Okay, and then we're going to solve. We're going to determine various things. We're going to determine the normal force in particular. Okay, so what we're going to do is we want to add, there's going to be a weight and there's going to be a normal force, and we're going to add these up and determine the net force. Okay, and so what we do when we do this kind of procedure is we just draw a dashed line at the same angle as the incline, as just like a reference line when we're drawing these vectors. So this angle here is the same as that angle. And then we ask ourselves, well, what are the forces acting on our object of interest here that's going to be accelerating down? Well, we always think two things. We think field force, contact force. What are the field forces acting on this block? Well, there's a weight pulling down, which has magnitude mg, and it's pointing straight down. Okay, so there's a weight pulling down of magnitude mg. And then there's a normal force. Remember, that surface is frictionless. It can exert a force on our car only in a direction perpendicular to the inclined plane, or to the banked road. Okay, and so we know that our normal vector is, starts here. We're adding weight plus normal, so it starts here and it goes for some length, and then we have to think, well, what is the length? Should we stop it here? Should we make it that long? Should we make it that long? How long should we make it? Well, we know that the total force, weight plus normal, better add up to a force that's in the direction of the acceleration. And the direction of the acceleration is that dashed line. So we know immediately, yes, the normal force must be in this direction, so at an angle theta, relative to the weight, and of exactly that length, so that weight plus normal force results in a net force, which is exactly down the incline. So let me put that in a different color. Okay, so this is the net force, the sum of all the forces. Okay, and that sum of all the forces is equal to the mass of the car, the inertial mass, times its acceleration down the incline. Okay. So we're not interested in the acceleration down the incline. We know that answer. We want to figure out what the normal force is. So I'm going to write that down. So right from here, you can read off, well, if that's the hypotenuse of our right-angled triangle, then the magnitude of the normal force, the side of that triangle, is the hypotenuse weight times cos theta. So we have this result, that the magnitude of the normal force is the weight times cosine of theta. Okay, so that's the magnitude of the normal force in this case. Okay? We're going to come back to this. One thing I want you to notice about this is that the normal force, the magnitude of the normal force, decreases as theta increases. So the normal force decreases, arrow pointing down, as theta increases. That's an important little observation. And that's clear because when theta is 0, then it's the full weight. The normal force is the full weight of the car. As you crank up the angle like this, the component of the weight that's perpendicular to the road, pushing the road in, compressing the atoms, they spring back out, is less and less and less. So the normal force starts equal to the weight and decreases to 0 if the road banks at 90 degrees. Okay? So normal decreases as theta increases. Okay? Now we're going to compare that to the second case. We're going to get a little bit more complicated now. So now we're going to say, yes, instead of the car just starting at rest on a frictionless banked curve, we're going to suppose that the car is moving around this in uniform circular motion, a horizontal circle. It's moving around on a frictionless banked curve in such a way and at a very particular critical speed in that circular motion so that it actually doesn't slide down or accelerate down as it goes around, or accelerate up as it goes around. We're looking for the special speed. Okay, so now let's first of all draw the picture. We have to draw pictures, three-dimensional pictures. Okay, so let's take the road. Yeah, space is always limited here, but okay, so we've got the road. Yeah, okay, let's do it here. So here is the banked road. Okay, banked at the same angle theta. And we've got a car of mass m on that road. And the coefficient of friction between the tires and the road is 0. It's a frictionless surface. Okay, but now instead of compared to this situation, we're going to let that car move around a circle. So it's coming out at this instant of time. It's coming right out at you. Okay, and so then it goes right out at you, and it goes around a banked curve. Okay, and so I'll draw that circle. This is a horizontal circle, okay? And this is the center of the circle, and this is the radius of the circle, r, and it's moving around with a speed v. In fact, we're going to call that speed a very critical speed v0, and the question is, what is that speed? The point is that maybe you can see this intuitively, or maybe not, but there is a critical speed v0 at which this car can drive around in circular motion, circle of radius r with speed v0, so that it doesn't slide up, like accelerate up or down, okay, as it goes around in that circle. Okay? All we really need is that the net force be a force directed towards the center of the circle and of magnitude m v squared divided by r. Okay? So that's the idea. So the question is, what is that critical v0? Too fast, it will accelerate up as it's going around. Too slow, it will accelerate down. Like here, when it's at rest, it'll just accelerate down. Okay, we start going around and around. If it's too slow, it'll still accelerate down as it goes around. If it's too fast, it will start accelerating up as it goes around. What's that critical speed? Okay, not too fast, not too slow. Now, the crucial thing about this is the following. We're talking about uniform circular motion. Okay, so whether you're dealing with uniform circular motion in a horizontal plane, or in a vertical plane, or in a plane tilted at some angle like this, no matter what the forces are, gravity and normal force and maybe static friction force and so on, whatever those forces are, they better add up to a force that at every instant of time points directly towards the center of the circle, okay, and has magnitude m times the centripetal acceleration v squared over r. Okay, horizontal circle, vertical circle, circle at any angle, all the forces at any instant have to add up to mv squared over r towards the center. Okay, that's a crucial aspect about circular motion. So what we're trying to do is we're saying, yes, well, what are the forces acting? Okay, that's going to cause that acceleration towards the center. And we put in that acceleration towards the center of the circle. That's acceleration. Okay. Well, what are those forces? Well, they're the same as in this case. So what we have is a weight, okay, and that's always present. And then we have the car. There's a contact force. The tires are touching the inclined plane. So the inclined plane is going to exert a force on those tires. And because that surface is frictionless, the direction of that force is only perpendicular to the surface. There's only a normal force. There's no tangential friction forces acting. Okay? So we only have two forces, exactly the same picture here, except something crucial changes about the picture. We have the same weight. Yep, there's our weight pointing down. Okay, let's draw our incline. Okay, let's draw a dashed line, a reference line at the same angle as our incline. And then, so we know we're going to add the weight plus the normal vector, tip to tail. Okay, and so the normal vector is certainly in that direction. We know that. It's perpendicular to the incline. And then the question is, well, how long is it? Well, if we make it the same length as in this picture, then the net force will be that way. Well, that's tilted down. We need a net force that's horizontal towards the center of the circle. Okay, so the net force has to be exactly horizontal. Okay, so it has to be on that line, which means that the length of the normal vector, we immediately determine that to be that long. Okay, so that long, such that the net force, get out my orange one again, the net force, weight plus normal, is a force that's exactly horizontal. So that net force is equal to the mass times the acceleration, and that acceleration in this case is centripetal acceleration directed towards the center of the circle. Okay, great. So that's that. So what else? I should write here, towards the center of the circle. Okay, and so now we have, instead of the normal equal weight times cos theta, what is the magnitude of the normal force now? The normal force is now the hypotenuse of the triangle. And so we know that the normal times cos theta is equal to the weight. Or the normal is the weight divided by cos theta, not times cos theta. So in this case, the normal, I'll just run out of room here. So the normal is equal to the weight divided by cosine of theta. Okay, so that's different than that. Okay, so in this case, what you notice is that when the angle theta increases, then the magnitude of the normal force decreases. It is the opposite behavior. Okay? Sorry, I said that wrong. Increases. Okay, so when theta is equal to 0, then the normal force is just equal to the weight, exactly the same as before. Okay, obviously when it's like this, then the normal force is just equal to the weight. Okay, but as we increase theta, crank this thing up, cos theta gets smaller, and it's in the denominator, so the normal force gets bigger than the weight, okay, instead of getting smaller than the weight. Okay, so as the angle theta increases, the normal force also increases, and we'll see why this happens. Okay, so great. So then the next thing we do is we say, oh, look at our triangle here. So since we know the weight and we know the angle theta, we can determine the magnitude of the net force. That's just that side of the triangle. And we set that equal to mass times the centripetal acceleration, v squared over r, magnitude-wise. Okay, so how much room do I need for this? Oh, not much. Okay. Should have put this down here. Okay, anyways. So, so now we say the net force, sum of all the forces, take the magnitude of that. That's the length of that side of the triangle. So what is the length of that side of the triangle? Well, you take the hypotenuse times cos theta will give you that. Hypotenuse times sine theta will give you that. So the hypotenuse is n times sine theta. Okay? And the normal is the weight divided by cos theta times sine theta will be the weight times sine over cos is tan theta. Okay? So the net force, the magnitude of the net force directed toward the center of the circle, is the weight times tan theta, which is the slope of the banked curve. Okay? So we got that. So the weight is mg. Okay? And then the idea is that net force towards the center is equal to the inertial mass of the car times the centripetal acceleration. So that's mass times the magnitude of centripetal acceleration is v squared divided by r. So in this case, we're looking for a particular v, v0. Okay? Great. So that's that. So we basically are demanding this for uniform circular motion. Okay, and then we just solve this. So the solution for v0, notice that the m cancels out. And m's often cancel out in things, and that's an interesting result. It tells you that your answer for the maximum, for the critical speed that a car can drive around a circle of given radius and given incline angle, that critical speed is independent of the mass of the car. You could have a light little sports car doing that at that speed, or you could have a heavy transport truck doing that at the same speed. Okay, completely independent. These are interesting observations that, as you start thinking like a physicist, you start to make. Okay, awesome. Okay, so now we solve for v0. So v0 is just g times r times tan theta square root. So we get v0 that critical speed, not too fast, not too slow, is equal to the square root of g times r times the slope, tan theta. Okay, and then what you do is, so that's the answer. And so if you were, at high school, you would say, oh yes, my r is 42 meters, my angle is 27 degrees, I plug this in, and that's my answer. Okay, but now what we want to do as physicists is we want to say, okay, well, does this thing even make any sense? Okay, and so what we do is we consider, say, for example, two special cases. Okay, so the first special case is what happens when the bank angle is 0. So we take the bank all the way down to 0 degrees. So tan of 0 is 0, and so that critical speed is 0 when the bank angle theta is equal to 0. And then you have to ask yourself, does that make any sense? What is that thing trying to tell you? Well, it does make sense. Okay, so this is how. If the bank angle is down to 0, what we're really asking is that a car be able to move around in a horizontal circle, okay, at constant speed. Okay. Now, if you think about that, and it's frictionless. That's the key point. And the answer is, how fast could you do that? Well, the answer is obviously 0. Okay, because if you start, suppose the car starts. It's tricky how to even get the car started because it's a frictionless surface. If it starts at rest, it can't even get going. The tires will just spin. Okay, but let's suppose that someone has come along and they got ice cleats or whatever, and then they push on that car. And so now you have an object which is sliding on a frictionless surface like this. And its natural state of motion is to continue moving with that constant velocity, so constant speed along a straight line. Okay, and then if you're in that car moving along like this on that straight line, you're saying, well, wait a minute, we're moving at some speed and we're supposed to go in a circle. So you turn your wheels. Well, your front wheels, there's no friction. There's no static friction between the front wheels and the road. So the road can't exert a force this way on your car. It can't exert a sideways force to bend the trajectory of your car away from straight line motion to curved motion. The road can't push this way. Okay, and so because there's no friction. And so you can't go at any speed on a horizontal surface, frictionless surface, okay, in circular motion. Great, so that makes sense. And then you consider the other case. You consider the case where theta approaches, 90 degrees, okay, or equals 90 degrees or whatever. So now the thing is this. Now you've cranked this thing. Well, first of all, what this thing says is when theta is 90 degrees, tan of theta is infinite. The slope is infinite. Okay, and so this becomes infinite. So it's saying that in order to, if you crank up the bank angle of the road to nearly 90 degrees like this, really steep, then you're going to easily slide down. In order for you to move in a uniform circular motion around that very steeply banked cone, you have to be moving almost at infinite speed, like very, very large speed. And as the bank angle approaches 90 degrees, then the speed that you have to go around is infinite. Okay? And so that makes sense. Okay? And then you can consider in-between angles, what happens at 45 degrees. At 45 degrees, tan theta is 1, the slope is 1, it's just the square root of gr. And then you could plug in some numbers and see, oh yeah, that's all very interesting. Okay, but these are the two important cases to look at. Does your formula make any sense? Okay? And that's it. Okay, so good. So we do have a little bit of room down here. So I'm going to do it this way. I'll draw the diagram down here for case C. Now this is an important case. So this was just sort of like warm-up exercise. Now we're going to do the really interesting case, okay? Where we're going to, the more realistic case is where it's not a frictionless surface, but it's a surface where there is a coefficient of static friction, mu s, between the tires and the road. Okay? Right. So let's just draw the picture first, and then we'll talk a little bit more about that. So now we have the same banked curve. Yeah, same banked curve. Like that. And it's banked at some angle theta. And we've got our car, okay, an object of mass m. And we've got a coefficient of static friction, mu s. Now you might wonder, This car is in motion. There's something dynamic happening here. Why aren't we dealing with kinetic friction? Why are we dealing with static friction? Super important point. The important point is that when the car is going around this curve, the wheels are turning. The wheels are turning like this, but every time a chunk of rubber from that wheel hits the road, that chunk of rubber is momentarily at rest with respect to the road. There's no slipping happening. Whenever you have two surfaces that are sliding relative to each other, the kind of friction you're dealing with is kinetic friction, and its value is mu k times the normal force when you're sliding. But if there's no sliding, if the one surface against the other surface is not, there's no relative motion, then you're dealing with static friction. Okay? And you don't know what the static friction is. There's no formula for static friction. You have to solve the dynamical equations. Okay? But you do have a formula for the maximum static friction, which is mu s times the normal. Okay? So yeah, I'll come back to that in a second. So we're dealing with static friction, not kinetic friction. Very important, because every time the rubber hits the road, it is at rest with respect to the road. There's no sliding happening. Okay, so we got that. And what else should we say? Okay, so now let's draw our circular motion. Remember, the car's coming out at you at some speed. It's moving around in this circular path. This is the center of the circle. The circle has radius r, and the car is moving with some constant speed. And that speed is going to be bigger than this speed over here in general. Okay? And so the question we're going to ask is, how fast, what is the maximum speed that you can whip around that horizontal circle without breaking static friction and starting to slide up, accelerate up? Okay, so we're looking for what is Vmax. So Vmax equals question mark. Okay, and here's the so let's go through this again here. So when we had a frictionless surface at some angle, okay, we found that, yep, if we go at that critical angle, square root of g r tan theta, if we go at that critical angle, if we go at that critical speed, then we can go around that surface, that circle, okay, with zero friction. If we were to be going at a faster speed, then what's going to happen is you're going to start accelerating up the incline at the same time as you're moving around in a circle, and so you're going to go sort of spiral up in bigger and bigger circles. Okay, it'll kind of go like that. And so if you're going faster than that critical speed, you're going too fast, and there's a tendency for your car to accelerate up. And so what you need is a force, that here's where the force of static friction comes in. The force of static friction is what prevents the car from sliding up. Okay, so then the road will exert a force on the bottom of the tires that way, force of static friction. Okay, and you can see why that's the case, because there is a tendency for those wheels, that rubber touches the road surface, and when it touches the road surface, it's momentarily at rest with respect to the road surface. There is a tendency for the car to want to go like this. That means that the atoms in the rubber are pushing on the atoms in the top of the road that way. All atoms are connected by little springs. Okay, a simple sort of model that you can construct of them. So those atoms in the road are shifted up like this. Okay, and they're all like springy, and so a spring has been compressed in this direction, and so that spring is pushing back in that direction. So the road molecules, the road atoms they've been shifted over. They're really pushing this way on the bottom of the tires. Understand that physically. Okay, that's the origin. That's why we need static friction, and that's its physical origin. Great. So that means we're going to have, what are the forces? Well, there's going to be a weight, there's going to be a normal force, and then there's an important static friction force that the road exerts on the car in that direction, down the incline. Okay, so let's now construct our diagram. Can we construct our diagram here? No, let's construct it here, because it's a super important diagram. We need to draw it a little bit bigger. Okay, so again, what we do is we draw a dashed line, okay, which represents the, let's draw it about here. A dashed line, which represents our incline, the angle of our incline. And what we're trying to do is we're trying to add up all the forces. Net force is mass times acceleration. So we're going to add up all the forces tip to tail, force vectors, and they better add up to a force in the direction of the acceleration. Whenever you have uniform circular motion, horizontal circle, vertical circle, circle at an angle, at every instant of time, that net force, whether it's gravity, whatever, they better add up to a force that's pointed towards the center of the circle. Okay, so the acceleration is in the direction towards the center. Great. So let's add them all up. So the first one is the weight. How big do I want to draw this? Draw it about that big. So the weight is down, magnitude mg. And then there is, in this frictionless case, there was only a normal force. But now we're dealing with static friction, so there's a normal force and a force of static friction going down there. So let's draw the normal force first. Let me see if I'm going to make this a little bit bigger. So the weight is down like that. And then we're going to add a normal force, and that normal force has to be perpendicular to our incline. So we know that the normal force, weight plus normal is going to start down here and it's going to go up a certain length. The question is, how far? Well, suppose that we made it this far. Okay? That was the normal force. Okay? So then we would have weight plus normal plus static friction. We know static friction is pointing down the incline. Weight plus normal plus static friction would end us up over here. So the net force would be in that direction. Wrong. The net force has to be exactly horizontal towards the center of the circle. Some water here. Great. So the normal force is not that long. Is the normal force this long? So just at the horizontal here, is it that long? Well, let's see. Then we would have weight plus normal plus force of static friction would take us down here. Again, that's not exactly horizontal. So this is the horizontal here. Okay, so the normal force, if the normal force were up to there, we would be dealing with exactly this situation. Weight normal so that the net force is horizontal. Weight normal so the net force would be horizontal. But wait a minute, we're adding a static friction force. Okay, so in this case is in fact exactly the same as this case. So this is the case B, where V is equal to V0, that critical speed that it can go around at where the coefficient of friction is 0. Okay, so if we had weight plus normal, then yeah, we could get a force directed towards the center of the circle and have circular motion without adding any static friction to this diagram. So then you say, well, now what we're really trying to do is say, well, we're going at that critical speed, but now we want to crank it up. We want to go faster. We want to take advantage of static friction preventing us from sliding up. Okay? So now what we do is we crank up the speed. And if we crank up the speed, we also crank up the normal force. So the normal force goes past this point. Okay, so let me just make sure I'm drawing that nicely. Okay, so it goes past that point. Suppose that it goes up to, say, just this point. Okay, so we're going faster than this critical speed V0. The normal force has grown larger. And then you ask yourself the question, well, how much static friction down the incline is required to keep it moving in this uniform circular motion? Well, it'll be this guy. Okay, this force of static friction is parallel to the, and down the incline. Okay, but then we say, well, let's crank up the speed even more. Let's crank up the speed to this, like really, really fast. Now the normal force gets even longer. It gets this long. The force of static friction still points down the incline, and it points exactly long enough so that the net force is horizontal towards the center of the circle. Okay, so you can see as you increase the speed, you increase normal from here to here to here to here, and so the force of static friction gets longer and longer and longer. Eventually you'll get to a point where you reach Fs max. And if you go any faster, then you break static friction and you start sliding up. Okay, so let's call this one Fs max. Okay, great. So we have weight plus normal plus a force of static friction, and we're right at the limit of Fs max, and that will allow us to calculate what that speed Vmax is. Okay. What else should I say? So this is in the direction of increase. increasing the speed beyond v0. Okay? And what else should we say on there? We should also add the net force. Okay? So we know the normal direction is that way. It's bigger than this, goes beyond that, and then we add force of static friction, so we get a net force that is exactly horizontal, and hence directed exactly towards the center of the circle. So this guy is our net force, sum of the forces. And that thing should equal the inertial mass of the car times the acceleration towards the center, centripetal acceleration, center of the circle. Okay? Great. So this is a really cool diagram. Okay, make sure you understand that kind of stuff. Okay, so now we say, yes, how do we solve for, I think we'll have enough room. Let's do it down, thing is we kind of need, well, okay, let's start, maybe we'll just start it down here. Okay, so we just sort of go all over the board. So now what we're going to do is we're going to calculate the weight. We're going to express the weight in terms of the normal force and the static friction force and the angles and all that. So we say weight. Just stare at this picture here. Remember, you can redo this example on your own in terms of x, y components if you like. And I recommend choosing one, the I hat, say, parallel to the banked curve, parallel to the road, and j hat perpendicular to the road. Go through the same example, but splitting it into components, and see that you'll get the same answer. But hopefully this is a little bit clearer, makes the physics a bit more clear. Anyways, weight. So the weight here, what's the length of that side of the triangle? Well, it's the length of this whole thing from here to here. Okay, and so it's the hypotenuse, the normal, times cosine of angle theta will take us from here to here. Okay, so that's normal times cosine. Okay, that's that distance. Okay, and then we want to subtract that little distance, and that will give us the weight. That little distance is this side of the triangle. Okay, so if that angle there is theta, then this angle over here is theta. And so the length of this side here, that guy over there, is equal to the hypotenuse, magnitude of Fs max, times sine theta. So this will be minus Fs max times sine theta. Okay? And remember, we don't have a formula for Fs. It's not mu s times the normal. That's Fs max. So Fs max, we do have a formula. It's equal to mu s times the normal. So this term is proportional to the normal. This term is proportional to the normal. Let's factor out the normal. In fact, what we'll factor will be a little bit more clever. Okay, and because in the end we want not sines and cosines but tangents, because remember it's the tangent of those critical angles theta s that we're interested in. Okay, so let's factor out n times cos theta from this expression. So n times cos theta times 1. Okay, that'll give that first term. To get the second term, there'll be a minus sign. There'll be a mu s, and then we have an n sine theta. Okay, so here we have an n cos theta. To get an n sine theta, we have to multiply by tangent of theta. Okay, so, cosine of theta. Okay, so cosine of theta times tan theta. Tan is sine over cos. Cos times sine over cos is sine. And then we'll get an n, a negative mu s n sine theta. Okay, just so factor it out like that. Okay, and so then what does that tell you? It tells you that, let me just bring this guy all the way up to here, and I'll write down this important result over here. Okay, so now we solve. So now we solve for the normal. So the normal force is equal to, okay, solving for the normal, it's just equal to the weight divided by this chunk. So it's the weight divided by cos theta divided by that thing in parentheses. So in the numerator, we have weight divided by cos theta. In the denominator, we have those parentheses. 1 minus mu s tan theta. Okay, so now that's interesting. Let's compare. Here, the normal force was just weight times cos theta. Normal decreased as angle theta increased. Here we had normal is the weight divided by cos theta. As we crank up the angle, the normal force increases. Now here we have the normal force is equal to weight divided by cos theta, that's this term in the numerator, and then corrected by this term. You'll notice that when we set the coefficient of static friction equal to 0, that drops out. And our formula for the normal force becomes the same as it was in this case. So as you get it more and more complicated, check that your results agree with your later results, more complicated results, reduce to your earlier results. Okay? Great. And so now what we do is we solve. Okay, so now we're going to figure out, well, what is that net force now? And we'll set that equal to the mass times the centripetal acceleration. Okay, so let's do that. So the sum of all the forces, the net force, its magnitude, the length of that line in that geometrical picture there, is going to be what? Well, it's going to be the length of that line is equal to that plus that. What's that? Oh, well, we look, here's a diagonal here. If we go the length of the normal vector times cosine of theta gives us this. The length of the normal vector times sine of the angle theta will give us that. So it's n sine theta. Okay. And then that's that part. Now we need to add that part. So plus, well, what's that? Well, we take the hypotenuse, Fs max, times cosine of theta. So that's plus Fs max times cos of the angle theta. So we got that. Now, let me try to squeeze this in here. So what we're going to factor out of this is an n cos theta. Okay, so I'm being a little bit clever here. Okay, if you work on this a little bit, you'll see that in fact this is the best way to write the answer. Okay, so as you get more experience with these problems, I want to factor out n cos theta. So to convert an n cos theta to an n sine theta, I have to multiply by tangent of theta. So this is tan theta. Sine over cos times cos is sine. This is n sine theta is what I've written down. Plus, remember that we don't have a formula for Fs, but we do have a formula for Fs max, and it's equal to mu s times the normal. Okay, so here we have a normal times mu s cos. Okay, and yeah, that's right, normal times mu s cos. So all we have is a mu s. Okay, so it looks like that. Okay, and then you say, well, what's that? Well, n times cos theta, we figured out what the normal force is. It's right here. Normal force is equal to this junk. And so it's the normal force times cos theta. If you multiply this expression by cos theta, that cos theta disappears. And so you just have the weight divided by that thing in brackets times that thing in brackets. So what you end up with is, in the numerator, you end up with tan theta plus mu s. In the denominator, you end up with this guy, 1 minus mu s tan theta times the weight. Okay? So the net force is proportional to the weight with some weird factor here. Now, here's where trig comes in. If you're really familiar with trig, you'd look at this thing and say, oh, wait a minute, there's a simple trig identity for this. You also have to remember that what is mu s? Mu s, the coefficient of static friction, is the slope of the critical angle at which an object starts to slip down. Okay, and we talked about that before. So we have mu s. So all of these examples are sort of building on each other. Mu s is tan theta s. Remember that from the other lecture. Okay, so we can write the numerator as, let's flip the order here. Mu s is tan theta s, okay, plus tan theta, divided by 1 minus mu s is tan theta s times tan theta times the weight. Okay, now at this point, you can see, if you know a little bit of trig identities, you can see, oh, well, that's just tan of theta plus theta s. Okay, this is a really interesting formula, a formula that's exactly like this, except instead of tangent functions, it's hyperbolic tangent functions. Formula exactly like this is the velocity addition formula in Einstein's special relativity. So these sorts of things you should just get practice at and see them, okay, and start getting a little bit more sophisticated in your trig. Okay, so the weight is equal to mg, and tan alpha plus tan beta divided by 1 minus tan alpha tan beta is tan of the sum. Okay, so it's tangent of theta, what order do I write it in? Theta plus theta s. Okay, so that's the net force. Okay, so we just did a little bit of simple geometry here. Okay, and we did a trig identity over here, and then we ended up with this. Okay, and now so that's the net force. We have to set that equal to that net force is causing the car to accelerate towards the center of the circle, and that net force is proportional to, it's equal to the mass, the inertial mass, times the magnitude of the acceleration towards the center, which is centripetal acceleration, which is v squared divided by r. What velocity are we dealing with here? Well, v max. So we'll write v max. That's what we're actually trying to solve for, is v max. Okay, so great. So again, just like in the previous case, notice that the mass of the vehicle disappears. Could be a little light sports car, could be a heavy transport truck. Answer is the same. They can go at exactly the same maximum speed before slipping up. Okay. And so then we solve for this, and we solve for Vmax. And so what we get is Vmax is equal to, just take R. So it's G times R times tan of that sum, square root. So it's the square root of, I want to write it the same way, GR. G times R times tan of theta plus theta static. Remember that theta static is the angle at which we have to tilt the road so that it breaks static friction, right at that angle right there. That's theta static. Okay, great. And then, so this is Vmax, and you'll notice that when the coefficient of static friction is 0, okay, that's 0, then tan theta s is 0. Okay, so theta s is 0. And then this formula reduces to this formula. What's the maximum speed you can go out without breaking static friction? Well, there's no static friction, so you're at that point, and this formula reduces to this formula when mu s goes to 0 and theta s goes to 0. Check, right? So we're getting more and more complicated, but we're checking back with the earlier expressions, right? So all along the way, you're always doing checks like that so that you know that you're right. You haven't made a mistake in your calculations, okay? And so then comes the interesting question. So Vmax, the question is, for what value of, what are the conditions under which Vmax goes to infinity? That's the question. So is it possible, like one answer, an obvious guess would be, if I wanted to drive my car infinitely fast, unlimitedly fast around this banked curve, even if there's static friction, you might think, well, the road has to be strictly vertical like this, okay, like 90 degrees to like whip around at infinite speed without sliding up, okay? But we see that that's actually not the case, okay? Again, the math is telling us here that Vmax will become infinite when tan of this angle becomes infinite. Well, so when it's 90 degrees, the slope is infinite, okay? So that happens when theta plus theta s is equal to 90 degrees. Or in other words, if the bank angle is equal to 90 degrees minus the static friction angle, or of course greater than that, okay? If you're at this angle, if the bank angle is this angle or steeper, you can actually go around that, that banked curve at infinite speed, arbitrarily large speed without breaking static friction and sliding up. Now, what I'm hoping is that this answer looks exactly familiar to the previous example. Let me just first of all draw the picture. So what it means is we've got, here is the ground. Here is, suppose that this is theta static, say at about 30 degrees. So this is the angle at which you would, if the car's at rest, you would break static friction, okay? Now, we're not interested in theta s. We're interested in, does it even look like an s? Theta s. We're interested in 90 minus theta s. This is 90 minus theta s. That's 90. 90 minus theta s is like this. So this is 90 minus the static limit angle. So if the car is zipping around on a banked curve that's 90 minus theta s or steeper, then that car can whip around at speeds approaching infinity. You can go as fast as you like without it slipping up. Okay, it's obvious that you can go as fast as you want without slipping up if the bank angle is like, approaches 90 degrees, it's 90 degrees. Okay, but this is saying the interesting thing that doesn't really have to be at 90 degrees. It can be less than 90 degrees. And I want you to understand, I want you to connect with the previous example that we did, which was this, which we had an inclined plane like this, and we had a block sitting on that inclined plane. There's a coefficient of static friction between the block and the inclined plane, and we are applying an applied force Fa. And so so what we found in this example, we found that when this tilt angle of the inclined plane is equal to or greater than 90 minus theta s, you can actually apply infinite horizontal force without this thing breaking static friction and accelerating up. This example is identical to this example. So that's another advantage of solving problems in general. You'll see that actually in Phys 121, the dynamics part, there's actually only about maybe 3 problems in total, right? So there's a lot of connections between them, and you end up really just doing the same thing over and over and over again. So if you take like a little bit of an elevated view, don't plug numbers in, you'll start to get a bigger picture of what the basic physics is. And the basic physics is the same, is in all these problems, okay? So that's super cool. This is you think, that's a simple example of the bank curve, but it's filled with all kinds of rich physics. And you need to get a little bit better at math. You need to get better at visualizing things. You need to maybe learn some trig identities and so on. So all of this is encouraging you to go from high school level, crank her up a bit, okay? Because I'm trying to get you to ready for second year, where there will be no numbers and it'll look all like this, okay? Let's first do that kind of stuff in the simplest possible examples, uniform circular motion around a bank curve, yeah? Okay, awesome. I really like this example. All right.